let me begin with the brief introduction of myself. I started to work on the quasicrystal when I was in the United States. I had opportunity to spend 1 year in United States from 1986 to 1987, and I was at Harvard. And at that time, the quasicrystal research was actually very active in the United States, so I spent a very exciting year. And actually, I wrote a paper on the quasicrystals of the atoms with tetrahedrally coordinated atoms. But unfortunately, most of people did not notice it. So when I came back to Japan, I worked on the phasons in the quasicrystals. I was particularly interested in the structural change or instability or disorder and dynamics of associated with the phason degrees of freedom. And I believe that the phason is one of the most important concepts in understanding the physics of quasicrystals. So the phason is my favorite subject, but I will not talk about phasons today because we have a very excellent, beautiful review by Marc de Bossieux yesterday. And I moved to my present institute in 1999, and since around 2000, I have been working mainly on the electronic structure of quasicrystals. So I will talk about the stability mechanism of quasicrystals from electronic structure point of view. And this is my future plan. Actually, I am allowed to be absent from my university this year. So I am planning to spend a sabbatical at Stuttgart. So I hope to see you again somewhere in Europe during my stay. So far, we have many kinds of the quasicrystalline compounds. And these compounds are classified into the several families. For example, we have the aluminum-based alloys with transition element, which I call transition metal family, aluminum transition metal family. And we have the alloys without transition element, which I call Frank-Caspar family. And also we have a cadmium-related compound, which should be classified into the different family from the Frank-Caspar. So I call this one Psi family, which does not mean family of Ampan-Psi, but the family of Psi-type quasicrystals. Okay, so all of these systems are understood in terms of the Hume-Rothery mechanism. But I think our understanding is somewhat empirical or experimental. Here the key parameter is the number of valence electrons per atom, which is denoted as E/A. And it is empirically known that we have optimal value for E/A for stable quasicrystals. That means the valence electron number controls the stability of crystals. So let's see in more detail about what is the Hume-Rothery mechanism. In the Hume-Rothery mechanism, the key concept is the Fermi sphere-Brillouin zone interaction. In crystal or the ordered materials, electrons are diffracted, and interference between the diffracted waves induces a gap at the zone boundary. Here I have the dispersion curve for the nearly free electrons, and we have dispersion curves for the diffracted waves. And at the crossing point, we have the gap open. And in the electronic density of state, we have the peak and the dips. And actually, the free electron energy at the zone boundary is just between the peak and dip in the density of state. And if the state below the gap is occupied by electrons, we expect the gain of the boundary energy. And the maximal gain would be obtained if all the state is completely occupied by electrons. So in that case, the Fermi level comes here, and Fermi wave vector is corresponding to the just at the zone boundary, which is the bisecting plane of the reciprocal lattice vector. So we can, in other words, the Fermi, this is the radius of Fermi sphere, and this is the boundary of Brillouin zone. So if the Fermi sphere touches the Brillouin zone, we have the maximum stability. We can expect the maximum stability. And I think it's interesting to note that the touching Fermi sphere means the Fermi energy at the maximum of the density of states, not in the pseudo gap. Such a stability mechanism or gain of the boundary energy is realized in typical compounds, alloys that are copper and zinc alloys. And in this system, we have depending on the zinc concentration, we can change the E over A because the copper is monovalent and the zinc is divalent. And also depending on the concentration of zinc, we have several different crystalline structure. And this crystalline structure is consistent with the assumption that the Fermi sphere touches the Brillouin zone for these crystalline lattices. So that's why the copper zinc is a typical example of the Hume-Rothery mechanism, typical Hume-Rothery alloys. In the 3D solids, Fermi sphere touches the Brillouin zone only at a few points. So we have the very small peak and dips in the density of state. So the energy gain is not so remarkable. But in case of the icosahedral solids, we have the icosahedral distribution of the reciprocal lattice vectors, and we have a near spherical Brillouin zone. And this is the typical X-ray diffraction pattern that we have the very strong diffraction peaks here, which is it's very hard to see, but it is indexed as 21111 and 221001. And we have another diffraction peaks at a little bit larger wave vectors here. And by constructing the Brillouin zone with the bisecting plane of these wave vectors, we have such nearly spherical Brillouin zone. So if the Brillouin zone is nearly spherical, then and the Fermi sphere touches such nearly spherical Brillouin zone, gap will open everywhere on the Fermi surface. So that means we have a larger peak and dips and gain of the boundary energy. So usually the pseudo gap near the Fermi level is considered to be a signature of the Hume-Rothery stabilization of the system. But I think it should be checked more carefully. We might have some other possibility to have the very deep pseudo gaps. That's what I want to discuss in my talk. But the interesting thing is that the E over A ratio is the estimated, different value are estimated for aluminum transition metal family and Frank Casper and the Tsai family. And for aluminum transition metal family, the E over A is estimated as 1.7, as already mentioned by Ampan Tsai yesterday. And in that case, the Fermi sphere touches a little bit smaller Brillouin zone shown here. And for Frank Casper and the Tsai family, the E over A is around 2. So the Fermi sphere is a little bit larger. Then in this case, the Fermi sphere touches a little bit larger Brillouin zone. So it seems very reasonable to have a different kind of the different family of quasicrystals. But I think there are a lot of theoretical questions about this, such simple descriptions. First, we start from the nearly free electron model. So we should check if it is the nearly free electron model is correct enough for the aluminum transition metal alloys, because the transition metal should scatter the electrons more strongly, effectively. And also, I showed the gap is open at the zone boundary with by two-wave mixing. But in a condensed matter, usually we need we have to include the effect of multiple scattering to describe the electronic structure more correctly. So we should check the dynamical effect. And also the rigid band picture should be checked more carefully. In the case of the copper zinc alloys, it would be okay because copper and zinc is a neighbor in the periodic table. So they are very similar to each other in a chemical sense. The only difference is the number of electrons. But aluminum and transition metal, cadmium and ytterbium, they are far from each other in the periodic table. So they are very different in chemical nature. And also the values of E over A is somewhat very funny variables because it is never measured. No one measured this one. And E over A equals 1 to 1.7 for aluminum transition metal. This value is calculated by assuming the negative balance for transition metals proposed by Rayner many years ago. So, important question would be the physics behind the negative balance for transition metals. So, I would like to pose, question as follows. Is a Fermi sphere Brillouin zone matching the only reason for stabilizing the quasicrystals? That's what I want to discuss. But unfortunately, we are not able to calculate the electronic structure of quasicrystal itself because of a lack of the translational symmetry. So we usually calculate the electronic structure of the approximate, which is a complicated crystalline structure with large unit cell. But we believe that the atomic structure and the electronic characteristic properties of electronic structure is almost the same in quasicrystals and approximate. And in the aluminum transition metal case, this is the cubic approximate for aluminum, palladium, manganese, and this is calculated the electron density of state. And here I showed the partial density of state without transition metal D element component. And we have the very deep shoot gap near Fermi level. And actually, the strong Bragg scattering, which gives the pseudo Brillouin zone, the energy for the zone boundary wave vector come around here. So it is located at the peak of the density of state. But anyway, it is very close to the pseudo gap. So it seems reasonable to assume that the scattering by these wave vectors are responsible for the gap formation. But we should note that we have a transition metal D state near the Fermi level. That has a very huge component which cannot show here. So we should check more carefully the effect of the transition metal D states. And this is another example, the cadmium, ytterbium, calcium, strontium, and magnesium system. And this is calculated density of state for the approximate for cadmium, ytterbium, cadmium, calcium, and cadmium, strontium, and cadmium, magnesium. And you see we have a very shallow pseudo gap near the Fermi level for ytterbium, calcium, and strontium, but we have no pseudo gap at all for the magnesium. So what's the difference of these between these? All of these systems are isostructural. The only difference is the second element. And I show the partial density of state of the D component from the ytterbium, calcium, and strontium in red here. So for the magnesium, we have no D state here. So that is the reason why we have we don't have any pseudo gap at the Fermi level for cadmium magnesium. So hybridization of the unoccupied D state of ytterbium and calcium is very essential in this case. In the rest of my talk, I would like to show you another example where chemistry plays an important role. That is the aluminum, lithium, Bergman, and Zintel compounds. Bergman phase is approximate phase of aluminum copper lithium and aluminum zinc magnesium quasicrystals. And this one has the 160 atoms in a cubic cell, and structure consists of the PCC packing of so-called Bergman clusters. And actually we have some partial occupancy of aluminum copper and aluminum zinc in this system. But in this calculation, we assume that this partial site is only occupied by aluminum. So we construct the hypothetical binary system. So we have the successive atomic shell with icosahedral symmetry, and each atomic shell occupied by aluminum or lithium and aluminum, lithium, and so on. So for such binary system, we perform the electronic structure calculations. And this is the result. And see, for aluminum lithium system, we have the very deep pseudo gap near Fermi level. And actually the free electron energy calculated from the zone boundary wave vector is located here. So again, we have the free electron energy very close to the free electron energy at the zone boundary is very close to the pseudo gap. So it seems reasonable to assume that the strong scattering causes such a pseudo gap. But in aluminum magnesium case, we have only shallow pseudo gap here, and if the density of state looks like more looks like that of the nearly free electrons. So both of these systems has same structure. But we have a very deep pseudo gap in one case, but we have very shallow pseudo gap, or we have nearly free electron-like density of state on the other case. So it is very different. And Zintel compound is the aluminum lithium Zintel compound. It's a very simple structure, but which has a sodium thallium structure. And this structure is an ordered structure on a PCC structure. And it is interpreted as the interpenetrating diamond sublattices. If we assume the charge transfer from lithium to aluminum, because aluminum is more electronegative, then aluminum has 4 valence electrons. So that means aluminum looks like a pseudo-silicon atom. And this pseudo-silicon atom is placed on a diamond lattice. So the total electronic structure is expected to be very similar to the silicon diamond. And actually, this is the result. You see the very deep pseudo gap at the Fermi level. And if you look at the band dispersion curves, we have the band dispersion very similar to the silicon diamond case. But if we replace the lithium with magnesium, the electronic structure changes completely. This is the result, and density of state looks like nearly free electron density of state. And if you look at the boundary dispersion, the boundary dispersion is also almost the same as the free electrons. So that means in aluminum lithium case, this one is the semiconductor, almost semiconducting system. But this one is nearly free electron metals. What is the difference between the lithium and magnesium? And important factor determining the electronic structure is the scattering potential of ions. And the Fourier component of the scattering potential are decomposed into the form factor and structure factor. And the structure factor carries the purely geometric information. And the form factor carries the chemical information. And the form factor is the Fourier transform of the ionic potentials. And for the Bergman case and the Zintl case, we have completely the same structure. So that means the structure factor is all the same. Only difference is the form factor from the lithium or magnesium. So here is the form factor for aluminum, magnesium, and lithium. And you see the blue one is magnesium and the red one is aluminum. So they are very similar to each other. But lithium is very weak in comparison with the aluminum and magnesium. So that means lithium scatters electrons very weakly. And magnesium scatters electrons as strong as aluminum. So that's a difference. Okay, so again, lithium is weak scatterer. So that means that lithium behaves like vacancy. So then a potential landscape seen by electrons in the Zintl phase is the diamond for aluminum lithium case, because aluminum is placed on a diamond sublattice. But in case of the aluminum magnesium, potential landscape is for the BCC lattice, closed packed structure. And this is very general argument that porous network like diamond induces a strong covalent bonding. For example, the crystalline silicon, which has the diamond structure, and of course it is the semiconducting. But liquid silicon, just above the melting point, has the closed packed structure. And electronically, liquid silicon is metal. So closed packed structure is metal, but the porous network like a diamond structure gives the semiconductor. And all the same thing is realized in the Zintl phase. And to check this idea, we calculate the electronic structure of the hypothetical Bergman phase with vacant lithium magnesium site. So we here even deeper or more remarkable than the aluminum lithium case. So if the electron sees only the potential landscape made up from the aluminum substructures, very strong covalent bonding will be induced. So the pseudo gap in aluminum lithium compound is a consequence of a particular potential landscape, porous network in this case. So we call it a structure-induced covalent bond. And to realize the porous network inducing the strong covalent bond, in this case, the chemical declaration of the closed packed structure is very essential. So actually, if we look at the electron density map, we have some bonding charge between the aluminum atoms. Here we have the two aluminum atoms here and here, and this aluminum-aluminum bond is surrounded by 5 lithium sites. And the lithium site is behaves like a vacancy. So we have very porous structure here. And then the bonding between these aluminum is enhanced. This is the characteristic electronic structure of the Bergman phase. And similar situation is also realized other quasicrystal related compounds. This is the experimental result obtained by Kimura's group. They measured the electron density map by maximum entropy method, and for the alpha aluminum manganese silicon system, which is the approximate phase of quasicrystal, aluminum transition metal quasicrystal. And in this structure, we have the aluminum cluster, icosahedral aluminum cluster, but at the center of the cluster, we have no atoms at all. We have a vacancy at the center of the cluster. So that means that we have the porous network of aluminum here. Then we have some bonding charge between the aluminum on a cluster. So I think the porous structure-induced covalent bonding is rather general aspects in the compound which is related to the quasicrystals. This is my scientific conclusion. Fermi sphere Brillouin zone matching is necessary for electronic stabilization of quasicrystal, of course, because we have no example of quasicrystal without matching. And also, the Friedel oscillation in interatomic potential seems very essential for our quasi-periodic structure. And I will not discuss in detail, but the formation of the structure favoring the oscillatory interatomic potential is really consistent with the Fermi sphere Brillouin zone matching. But I want to stress that the purely geometric matching is not sufficient. And here we show the chemical decoration is essential. Structure-induced covalent bond is realized in some quasicrystal-related compounds. This is not scientific part. Let me tell you a little bit about the celebration of the 70th birthday in Japan. We celebrate the birthday of a particular age as a special event, and we have a special name for each of them. For example, the age of 60 called Kanreki, and age of 70 called Koki, and the age of 77, 80, 88, 90, 99, 100, and so on and so forth. We have special names for each of them. And for the age of 70, we have another name, which is not so popular, but we have another name, which is this one. And actually, this one comes from the long of the Analect of Confucius, a book written in ancient China. And this is what Confucius said to his disciples. And he said, at 70, I could follow my heart's wishes and did not make mistake. So, Danny, you can follow your heart's wishes. I'm sure you will not make mistake. So please continue to give us the advice and suggestion and message according to your heart's wishes. Okay, so we have a custom to make a gift on these occasions with special color. For the age of the 60, we make a gift with red color. And for 70s, we make a gift with purple color. This is my small purple gift for you.